die de Mexican, ga je daarmee completen. Ik ga beneden.
Sir, is there sugar? Are there sugar cubes? I think you didn't have a box of sugar cubes out there. Oh, they're out there.
Nee,
Oh.
nee, ja, she told me yesterday about that.
How you doing? Hi. I love sugar in all its forms. I love it. We went to a sugar factory in Hawaii. I read about the history of sugar in the world. It's a great commodity. It is a fantastic discovery. It's just a kind of a genetic variation of bamboo or something like that. On the other hand, at least historically speaking, colonial exploitation of labor and slavery, like that in its history. Do you have a mobile camera? Here's what I'm thinking. I kind of like everybody's amenable to the idea. Just stick a camera in their face and do a one shot of, hi, I'm so and so from so and so. I'm at an arcade. It's called blah blah. It's for the record, right? It's going to be on the Twitch forever, right?
It's streaming, yeah.
It's streaming and it's recording, correct?
Yes.
Is that possible? Like the 360 camera?
Yeah, that's we might have to wait.
That's
if Dicky comes in, it's his camera.
Oh, it's his.
And he's not here right now. I think it's going to be later. This one is supposed to be.
Does it have to be tethered for it to work?
No,
what am I looking at?
The power for it's supposed to be. It's on it's on battery, but battery runs out at some point. And then it goes to the server.
Okay,
But yeah, it can go without the cable. Yeah, good possibly use this.
as it's doing live stream.
If this one is not on the license, it's a backup stream. So we can use this as a
For the permanent record, but not as part of the live stream.
exactly.
Alright,
No, you would have to move them in front of this camera.
And that's tethered, obviously.
And that's yeah.
Right, okay.
That'll work.
No, that's fine. If Dickie happens to come by again and has it, and we can do it,
Right.
we'll do it. Otherwise, no.
Yeah. Or
Am I late?
we can always do it on Friday or Saturday, or it doesn't have to be
Right.
today. Yeah.
Right, correct. Oh, it is kind of start. Yeah, in a real way, Friday might be better because there'll be more people there.
Yes.
So that all be locally. Oh, there they are! Yeah, the Fortnite
Setups.
If there is no one,
Thank you.
morning.
Hi, good morning.
Morning.
Oh.
I need to take this one.
I think I'm.
Oh.
So never, ever, ever solder without using your safety glasses. Remember, I told you that yesterday. Is the camera rolling? Did you catch that yesterday when I said that? Don't ever solder without your safety glasses. All seriousness aside, once and only once in my life, I did splash some hot solder into my eyeball, and it hurt a lot. It felt like I opened my eyelid, poured in beach sand, closed it down, and that was it for days. It didn't do any permanent damage, but it really hurt. So, should you wear eye protection? Yes, you should. Do I? No, I don't. Well, actually, I kind of do because I have to wear glasses to see what the heck I'm doing. Give me a second to turn the camera on. I don't think we have quite as much sunlight today.
Yeah, I was with you.
Almost with you. Hey, Chris, did you have a chance to watch that homework that I sort of asked you to watch yesterday? The video?
I've got about halfway through it.
Oh, you did? Okay.
Yeah.
Finish it. Sorry, give me a second.
Excuse me.
Yeah.
I feel a small problem happened yesterday where the cord got burned.
Oh, it melted? Did it burn like this?
Not entirely through, but there's
Oh,
still
right there? Oh, no, that's something.
That's just it.
Inside that, there's another set of insulation. So, yeah, I don't know that.
It was just
Good point. Good safety point.
I think I may have manipulated it
That having been said, if it went all the way through, we have plenty of soldering. So I think you did great yesterday on the soldering deal. You said you could solder. You certainly can. Everybody can solder, which is great. The project that we're going to build today, this afternoon, we'll get to it later, is way more than what we did today or yesterday. You'll see. We'll talk about this afternoon, but I don't have to worry about your ability to construct it, which is. For me, it's like half the battle. Soldering is the most important skill of all. Really, if you can diagnose something, but you can't solder, you can't fix anything. So you have to do it with soldering, and it's really cool. So yesterday, the thing that you built, if you remember how it went, and there's a circuit description in that book, is that when you first built it, it went dee kind of fast back and forth. And then you changed the two resistors, and then it went slower, dee. So what we're going to delve into now is like your first real look at real electronic theory, sort of. I mean, how stuff really, really works and why it works and and stuff like that. So the thing that you built is a thing known as the RC time constant. This is like stage one, real electronics, how stuff actually works. And I think it's pretty interesting. I've always been fascinated by this thing ever since I learned about it. Here's the deal. If I have a circuit that consists of a resistor and a capacitor, and the resistor happens to be 1 million ohms, 1 mega, and the capacitor happens to be 1 microfarad, it will take exactly 1 second to charge up the capacitor if I try to stick some juice in on it. In other words, I connect that thing up, it's going to charge up the capacitor. But because there's a resistor in series, if you remember, in series, meaning the current has to go through one part to get to the other part, it's going to take exactly 1 second to charge up that capacitor. Doesn't matter what the voltage is here at all. If, for example, this was a 10 microfarad capacitor, it would take 10 seconds. That makes a lot more sense. That makes a lot of sense, doesn't it? If it has to go through the resistor first to fill this capacitor up, it's going to take longer to fill up a bigger capacitor. A capacitor is like a water tank. You know, how much, whatever its capacity is its microfarads. The more microfarads it has, the more of the charge in the store. It's just storing electrons and not water molecules. On the other hand, let's go back to 1 microfarad. If this resistor were 500 kilos, and in reality, they don't make a 500K resistor, not really. In the real world, you will see 470K resistors a lot, but you'll never see 500K in the real world. There's reasons for that. At the moment, you don't care about that. Then it would take a half a second. In other words, if I made the resistance smaller, that thing would fill up faster. Well, what you did yesterday was, remember, this was R4 and R6. And the original one is like something like 22K or something like that. And it went fast. And then you pulled those resistors out and you put in R4A. And you remember we put in R4A. And it went slower. Because it was like, I don't know, what is it, 36K? I don't know what the heck it was, 47K, whatever it was. It was larger and all. So this is something called the RC time constant, and that's how it works. The same exact thing is used to set the audio frequency. When you built the kit, there's that little timer chip. It's called a 555 timer. A 555. It's a very common integrated circuit. It's probably the world's most common IC. It's been around for half a century or something like that. It's ubiquitous, but it's really useful in lots of situations. And in this case, that's the thing that makes the audio. The audio was generated by the 555 timer chip. And there's a couple of pins there. And connected to that pin, there's resistors and there's capacitors. Only they're much smaller than this. They're much smaller. They're like the little picofarad capacitors and stuff like that, which makes a higher frequency that you can actually hear. It's not going just back and forth. It's audio tone. So anyway, there you go. So that's something known as the time constant. You with me so far? Right? Pretty simple. There's another place, critical place. It's like a preview of real monitor repair. There's another place in the monitor and it's in the horizontal output circuit. We'll talk. I'm relaxed for now. I told you every day is going to be a little more complicated, and today will be. But for the moment, just relax. There's another circuit. It's in the horizontal output circuit of the CRT monitor. It is the most, I guess you'd say, critical circuit in the monitor. It's where we have lots of bad stuff happening. I'm sure you've heard of things called flyback transformers flying apart and burning up, and flyback replacement is a common thing. If you're interested in this, you probably know about flyback transformers. Don't worry about it for now. We'll talk about it. But that's part of a whole tuned circuit. The whole horizontal output circuit, which is the hardest working circuit in the entire monitor, it's the thing that when it fails blows fuses and maybe even catches fire and stuff like that, and it just works the hardest. It's kind of a tuned circuit that consists of a different kind of a tuned circuit. It consists of a tuned circuit which includes a part known as an inductor, better known as a coil, or some coils really, and a capacitor, or some capacitors really. And a circuit that provides what's known as an LC time constant. I will definitely cover this again. If this doesn't make a lot of sense to you right now, just relax. I'm going to show you the stuff. But if I put a capacitor in parallel, if I put a capacitor in parallel with this part right here, the coil, which is technically known as an inductor, it forms this circuit that provides something known as an LC time constant. This circuit has a name. It's kind of a nickname. It's called a tank. I'm not sure why it's called a tank. I don't know why it's called a tank. But a coil is also an energy storage device. I showed you how I charged up the capacitor and it holds a charge and then it discharges into the light bulb. But a coil is also an energy storage device. It does it in a completely different way. It doesn't do it with aluminum foil and capacitors and stuff like that. It does it with magnetic fields. When you run current through a coil, it generates a magnetic field. It makes an electromagnet. So that's energy storage. This magnetic field is there. Then that magnetic field discharges into the capacitor and charges up the capacitor, however a capacitor charges. Then the capacitor discharges back into the coil, which generates another magnetic field, which discharges into the coil and makes a waveform and we're going to talk about waveforms tomorrow. A waveform is this is a simple graph I'm showing you that shows time in the horizontal direction versus voltage in the vertical direction. I'll explain more about it when we get to that point. It generates a signal that is a certain frequency. It generates a signal, a beautiful signal, that is a specific frequency depending on how big the capacitor is or small the capacitor is, and the size of the coil as well. We're going to talk a little bit about coils later on. They're not a failure item in general. Coils don't fail. It's just a coil of wire. It's just a coil of wire, so not much can go wrong with it. But a coil is abbreviated with the letter L. I know that seems silly because we use C for capacitor. We can't call it C, so they use L. It stands for another dead guy named Lenz, and I don't know what he did. But coils are abbreviated. If you look on any printed circuit board, you'll see a coil, and it'll say L25 or something, or whatever it happens to be. But it's like almost a zero failure item, except in the horizontal output circuit that we're going to talk about, this big bad circuit, where there are issues here. It's really the most complicated. I don't need to put a block in you. It is the most complicated part of the monitor, a place where we see it like a ton of So I just thought you'd be interested in seeing a couple of time constants, one of which you experienced, and you did, the RC time constant, and this is the LC time constant, which we'll look at later on. So today, mostly, we're going to concentrate on testing. How to test components to see if they're good or bad. Yesterday, we learned kind of what the parts are, but today, the most important thing is component testing, as far as I'm concerned, because as I mentioned to you previously, I got away with murder when I first started repairing stuff because I know what the parts are and I know how to test them to see if they're good or bad. In many cases, I'm not even sure what it does, but if you can tell me how to test it and what I should see, I'll be able to tell if it's good or bad. So that's kind of in a nutshell for today, mostly. We're going to talk about how stuff works as well, but we're going to really concentrate on testing. So you already know how to test resistors. You went through the stack of resistors right on the white card and so on. And remember how resistors fail, that bad resistors open circuit. When you test a resistor, when it goes bad, its resistance will always increase. It will never decrease. It will never short circuit. And that's just the nature of how they fail. So you already know how to test resistors, and then we're done. That's it. They hardly ever fail. You can try testing them in circuit. You can try testing every part in circuit. If it doesn't test right, you're going to pull it out to replace it. Whenever you take a part out, you always double check it. Always out of circuit. In circuit analysis might work, and it might not. You don't know. When you take something out, you think, oh, it's bad. I'm going to take it out. You're going to test it. Like I said yesterday, half the time you're going to go, oh, yeah, it's good, and stick it back in. Half the time you're going to go, yeah, it's definitely bad, and replace it. And you're done. I'm more of a parts replacer than anything. I mean, honest to goodness, I don't care if I throw 6 or 8 parts at something and then it magically works. I don't care which part fixed it, really. If that fixes it, I don't care. The parts are really cheap. So in this class, I'm going to show you how to get right down to the exact part. That's always my goal. My goal is to just find the best thing I can do. Is the most fun, really, is through some sort of analysis, you say, I think that part is bad, and it is. And you go, all right, great. You change the part and you're done. If it doesn't work, oh well. The parts are cheap. And if it doesn't fix the problem, maybe the thing you took out is still good, and now you have a spare part. Today you're going to learn how to test the parts, so for sure you'll know if the parts are good or bad. So let's go back to electrolytic capacitors. And remember, the real name of this thing is aluminum electrolytic capacitor. And the reason I'm stressing that's the real name is, like, if you're ordering it online, that's what you're looking for. If you just look for capacitor, there's 6,400 different capacitors that you can have, and you got to narrow it down. Aluminum electrolytic. So that's the number one. That's the number one failure. And here's the deal. Let me go back to this kind of common schematic symbol. This is really the most common schematic symbol for an electrolytic capacitor. And remember how it really works is that. Oh, let me make this bigger. Sorry. And remember, the way it works is that the positive plate of the capacitor is the one that's insulated. It's aluminum, but it's covered with aluminum oxide and it's insulated. And then there's this wet piece of paper that I'll try to illustrate in my terrible way, like that. The paper that's soaked in this stuff called electrolyte. So I think I mentioned it to you yesterday. You can kind of think of it like a liquid wire. I just think of it as like a liquid. It's more than that. Just think of it as a liquid wire, basically. So that is the actual cathode of the capacitor. technically speaking, that's called the cathode. The negative terminal of things are called cathodes. We're going to look at that word a lot today. But you can't solder to a wet piece of paper, obviously. So we have the negative plate here, which is just bare aluminum. It conducts electricity real cool. And the paper has to touch that negative plate, which is really what you're soldering to and like that. Everybody with me so far? That's the concept. So over time and with heat, that starts to dry out and it becomes a resistor. Ideally, it should have no resistance. It's a wire. It should have no resistance at all, but it does have some. And the older the capacitor gets, the more that dries out. We have a name for this resistance, and it's known as the capacitor's ESR. It's called its ESR. And before I go further, here's the thing that you need to remember. This is the thing. When it comes to ESR, low is good. Even if you don't understand anything about what we're about to discuss, and you will, the important thing to know is low is good, 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 low is good. Whatever this ESR thing is, you want it to be low. It's got to be low. Got to be low.
What means low?
So high is bad, right? High is bad, high ESR is bad, low ESR is good. That's the important thing. So ESR stands for equivalent series resistance. Equivalent series resistance. Equivalent series resistance, or ESR. And it's a real resistance. It's not a resistor, but it is exactly the same thing, electrically speaking. It's a resistance. Ideally, we'd like that to be zero. In a perfect world, it will be. And you may even measure these Michicon capacitors. You're going to make a tester today. Michicon capacitors have super low ESR. You might even see zero today. I don't know. It varies, but low is good. But as this dries out, that resistance increases. It's a quarter of an ohm, or it's a half an ohm, or 1 ohm, or 2 ohms, or whatever, as its resistance increases as it dries out over the years. The main thing that causes them to dry out mostly is heat and time. For every 10 degrees Celsius rise in temperature,